we will understand an effective algorithm to sketch curve of radicals. I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll discuss in details curve sketching algorithm. We have taken an example based on radical functions. It's a very important example seen in test papers where students normally struggle. The question is to sketch the graph of f of x, which is equal to x to the power of 1 over 3 times x minus 4 to the power of 2 over 3. Now, to sketch the graph, we should understand that it is a radical function, and therefore there will be points where the derivative will not be defined. And so we need to figure out the critical numbers. Anyway, let us look into the steps involved to sketch this particular graph. First thing which you should figure out is what are the intercepts. Both x-intercept and y-intercept. Now, intercepts will give you very good points to begin with. Then you can look into the domain of the function. As far as this function is concerned, the domain is all real numbers. And once you have these basics, then we can analyze the first derivative. So we'll find the first derivative. And from the first derivative, we can find local maximum and minimum. Then we can analyze the second derivative. That will give us concavity. Concavity really helps us to connect the dots. Fifth, label diagram. Put them all together. That is how you get a perfect sketch which can fetch you 100% marks, right? Well, in case you want to learn from me, you can always send an email on the address given. Most students are doing extremely well. They're right on top of their class, getting awards and scholarships.
After attending university. The winner of this year's Certificate of Achievement Schulich Leader Award is Akshi Kandivani.
Great. Our student Akshit gets highest marks and the most prestigious Schulich Leader Award. You can be there.
Join our classes and excel. Now, let's begin with finding the intercepts. So for the given function, what is an x-intercept? X-intercept means y value is equal to 0. So f of x is 0. So we'll write 0 equals to x to the power of 1 over 3 times x minus 4 to the power of 2 over 3. So each factor should be 0. That gives you x-intercept at x equals to 0 and at x equals to 4, correct? So we have two critical points here on the graph, which is 0, 0 and 4, 0. Now let's look into the y-intercepts. So y-intercept is very easy to figure out. Normally that is the first thing which you should do. That's the value and x is 0. So if I plug in 0, what do I get? I get 0. So that means that, yes, which we could have seen from here also, that means that the graph passed through origin. Well, in this case, both x and y intercept, we had already got it, but it's an algorithm, right? You have to follow some steps. So it's a very critical step. So we have figured out the x-intercepts and the y-intercept and two critical points on the graph. Domain, as I was saying, is all real numbers. So let me write down here. Domain has no restrictions, right? Perfect. So now let's move on and analyze the first derivative. So we'll have to apply the product rule. Derivative of x to the power of 1 over 3 is 1 over 3, x to the power of 1 over 3 minus 1, which will give me minus 2 over 3, correct? Times the second term, which is x minus 4 to the power of 2 over 3, plus first term, x to the power of 1 over 3 times derivative of the second term, which is 2 over 3 x minus 4 to the power of 2 over 3 minus 1, which is minus 1 over 3. So we got the derivative. That is not a difficult part, but finding the critical number is really difficult, since we need to now factor this, and factoring could be critical. So to factor, we see 1 over 3 is common factor, right? X to the power of minus 2 over 3 is also common. And you'll see that x minus 4 to the power of minus 1 over 3 is also common, right? Now, when I factor this, what do you get inside? From the first term, since we have x minus 4 to the power of 2 over 3 left, and when you add 1 over 3, you get x minus 4. And in the second term, we have already taken x minus 4 to the power of minus 1 over 3. We are left with 2. Let me write down times 2 and x value, right? 2x. So that gives you 1 over 3 to the power of minus 2 over 3 and all this, and we can simplify this, right? So let me rewrite here itself. Three x minus 4 and in the denominator we have 3 x to the power of minus 2 over 3 times x minus 4 to the power of 1 over 3. Does that make sense? Now, we can easily find the critical numbers. So what are the critical numbers? Critical numbers are numbers where the first derivative is going to be 0 or does not exist. So we're finding the critical number where the first derivative either is 0 or does not exist. So in this case, the critical number is at x equals to, the numerator is 0 for 4 over 3, right? And the denominator is 0 for x equals to 0 and 4. Now, many students are only working with stationary points. Stationary point is a point where the derivative is 0, right? So that is kind of incomplete definition for radicals, we have to use the critical numbers. And we have to take care of denominator being 0. You'll soon realize what will this result into. Correct? So denominator equals to 0 might result into vertical tangent. Note. F prime x does not exist may result in vertical tangent. That is very important to understand, right? Perfect. Okay. So let's take it to the next page to analyze the first derivative, right? So let me go to the next page so that we can analyze these points. So the first derivative which we got was, we get 3x minus 4 in the numerator, and then we had 3 times x to the power of minus, let's see, 2 over 3, I think, right? And x minus 4 to the power of 1 over 3. Well, that becomes plus, right? Because we took it in the denominator. Okay. So x to the power of 2 by 3 and x minus 4 to the power of 1 by 3, right? Minus this, correct. So that is there, and the critical numbers which we found were x equals to 4 by 3, 0 and 4. So let's analyze these critical numbers now. So we have 0, 4 by 3 and 4. Let's write them in a particular order. It's good to write like that, right? 0, 4 by 3 and 4. So the test points which we are going to take could be, let me write down here. Okay. So let me write down the test points on the left side of 0 as minus 1, on the right side as plus 1. This could be 2 and then 5, correct? We have to check these factors, which are 3x minus 4, 3 times x to the power of 2 over 3, and x minus 4 to the power of 1 over 3, correct? Now, as far as 3x minus 4 is concerned, if I write minus 1, we get a negative number. 1 will give me negative, 2, and 5 will give me positive. 3x squared root 3 will always be positive, right? Here, if I put minus 1, this is going to be negative, 1 will be negative, 2 will be negative, and 5 will result into a positive value. And therefore, the derivative as such will be positive, right? Again positive, here negative, and then positive. If there are 2 negatives, it results into positive. 2 negatives means even number of negatives when multiplied or divided will give you positive, and odd number of negatives will give you negative. So, if the first derivative is positive, that means that the graph is increasing, right? When negative, it will be decreasing. When positive, increasing. And clearly, we have a local maximum at a point where x is equals to 4 over 3, correct? And here, we have a local minimum where x is equal to 4, correct? You see? So from the analysis and this sign chart, sometimes we call this a sign chart, it is very clear that we do have local maximum at 4 by 3 and local minimum at 4, right? Now at 4 we know the function is 0. We can now calculate the value. What is the maximum value, correct? So let me write down. f of 4 by 3 and calculate the value. So substitute 4 by 3 in the equation, right? And calculate. So when I calculate this value, I get approximately 2.11. 2.1 we can write, right? So that becomes the maximum value. And we know at 4 it is 0, right? So this point we know, right? So we have one critical point, which is the local maximum. Now, so with this local maximum minimum, actually we have sufficient information to sketch the graph. Since we know it's a radical function, we can actually at this stage sketch the graph. So in the video, I'm avoiding the second derivative and concavity test, but from this information, I'm going to sketch it. You should try to confirm the result, finding the second derivative and the concavity. Perfect. So let's move forward and write down the information which we have got so far. So we know that the intercepts are at the origin, x-intercept, right? And we found 4, 0, another value. Then we have the local maximum value. Local maximum was at 4 over 3. The value was 2.1. And we had the local minimum, which was at the x-intercept 4, 0, right? A key information which also got was that the derivative, first derivative, does not exist at x equals to 0 and x equals to 4. Now, we'll use this information to sketch rather than concavity in this particular case. So, here's a rough sketch. Domain is all real numbers. So, when you look at origin and derivative is not defined, it means it's a vertical tangent here, right? And therefore, the graph nature should be what? Do you see like this? It goes vertical. Do you see that part? So, this vertical tangent reflects the first derivative does not exist. You get the idea. And then we have a maximum value at 4 by 3. So now it has to turn and come down, right? Where this value, which happens to be at 4 by 3, and we found that the value is 2.1, right? So that becomes the local maximum. Now, at 4, which is the x-intercept, we again find that the first derivative does not exist, right? So at this point, it is a cusp. Like you expect in radical function. So that is the characteristic of radical function. So how did I find this is a cusp? Because cusp is a characteristic of radical function. Do you understand? So radical functions have cusp in graph and vertical tangents and or, right? So this key information about the radical function helps us to sketch a graph. So now, that's a final graph. However, I'll request students to further go ahead, find the second derivative and check for concavity, right? Do you see that concave up? Here it is down, and here also it's down, right? So this concavity test can be done with the second derivative, which I request students to do. Make sense, right? So I hope with this you understand the complete strategy of sketching a radical function. Feel free to write your comments and suggestions. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.